In calculating the moment of inertia of a rod about its end, something I do expect you to be able to do, along with a couple of others, I saw integral from 0 to L of big M x squared dx. Okay? It's wrong. Now, it's not far off. The actual integral should be the same integral, but it's M over L times x squared dx. If you went through the process of setting up the integral and reasoning out the integral, I would be somewhat forgiving of that oversight. But if you didn't go through the process, I'd be much less forgiving in grading the test, because I expect you to use the process of setting up an integral in order to get an integral, rather than just memorizing what you think the integral might be. And there's a simple enough process to do this. We have a typical increment delta x at position x star relative to the end. What's the mass of that increment? What's the contribution of that increment to the moment of inertia? Well, the mass of that increment is in the same proportion to the mass of the total rod as the length of that increment is to the length of the rod. So it's easy to figure out that the contribution to the mass, the delta M, the mass in that delta x interval, is M over L times delta x. Very straightforward proportion, linear, and very, very, very easy to do. So there's your mass contribution, your contribution to the moment of inertia, and maybe I should call that delta I, is equal to delta M times r squared, where r is your distance from the axis of rotation. Well, if x star is measured relative to the axis of rotation, that's just your delta M, M over L delta x, multiplied by x star squared. Now, you're going to sum that up over all such integrals, and then you're going to take a limit as your delta x approaches 0. And it should be very clear to you from what you learned, or should have learned, in first year calculus. Not everybody learns it, but by the time you get to this point in this course, you should know it. You should be used to the process, and you should have applied it many times in developing these integrals. And of course, if you haven't done it now, you're going to really get to do it second semester. That sum is going to approach the integral from 0 to L of M over L x squared dx in a way that I'm not going to detail now, but you should be able to detail. And you should be able to justify all of those details. That's part of understanding the system you're engineering. So that would be the correct integral. Now, again, if somehow you left out the L there, but you went through the whole process and set it up, I might give you 7 points out of 10. If you just write this integral down wrong, you're going to maybe get 3 points out of 10. And of course, the main goal is to be able to do what you need to do to be a good scientist, a good engineer, a good mathematician, whatever. So you really need to understand how to set up integrals and how to derive integrals applying to various situations. Extremely important.